Hello, everyone. Thanks for joining. I'm Soubhik Kumar, a postdoc at Berkeley, and today I'm very excited to tell you about dark radiation isocurvature and the constraints we have derived on it, and also the role it can play in the context of the H-naught tension. So this is based on work in progress with Shubhajit Ghosh and Yushin Tsai, both at the University of Notre Dame. So as we know, based on the Planck observations, that the primordial perturbations, they are adiabatic, almost scale invariant, and Gaussian to a very high degree. And minimally, these properties, they point towards the paradigm of single field slow roll inflation. However, if you look at more UV complete models of inflation or high energy models of particle physics, then you realize that it's very plausible to have extra degrees of freedom or extra fields during inflation. In particular, it's quite natural to have extra light fields other than the inflaton during inflation. And one thing that can happen is that these light fields, they can inherit quantum fluctuations during inflation, and they can give rise to isocurvature perturbation. And if these light fields, they are very subdominant in energy, these fluctuations, they do not contribute to total isocurvature, but rather total curvature, but rather they give rise to this isocurvature perturbations. And a canonical example in this context is axion dark matter isocurvature, where axion can inherit this quantum fluctuations during inflation, and then eventually give rise to dark matter isocurvature. Now, Planck has searched for in general isocurvature perturbations in baryons, dark matter, and also in neutrinos. And roughly speaking, the constraints on these objects are of this order. So the isocurvature perturbation has to be less than the 10% of the curvature perturbation, very roughly speaking. Now, in this talk, I will focus on a scenario in which we have isocurvature perturbations in dark radiation instead. So as many of you know, dark radiation is very common in various extensions of the standard model. They can arise in various contexts. So here by dark radiation, I just mean ultralight degrees of freedom that are very weakly coupled to the standard model. For example, they could be dark photons, they could even be gravitational waves, and so on. Now, typically, to characterize the energy density in dark radiation, we parameterize via this famous Delton effective parameters, and a lot of constraints are based on that. And especially in the case where dark radiation perturbations are adiabatic, they are very well studied in the literature, and depending on their coupled or free streaming nature, there can be extra damping at high L or extra phase shifts for acoustic oscillations and so on. So there's a bunch of literature. Here I'm only citing a few of them, but there are many important literatures other than these as well. Okay, so now in this talk, I'll focus on this dark aspect of dark radiation. And the point is, because we call them dark radiation, they're naturally objects that are very weakly coupled to standard model. And that's why it's very easy to imagine scenarios in which this dark radiation comes from a field other than the inflaton during inflation. So for example, it could happen that the inflaton reheats into standard model, but then during inflation, there's a separate degree of freedom like a curvaton, which does not talk to the inflaton, but later on this curvaton decays and give rise to dark radiation. So what can happen is that this curvaton, through its fluctuation, can acquire isocurvature fluctuations during inflation, and later on, through curvaton decay, the isocurvature fluctuations can get imprinted into dark radiation. So that's the broad and that's the simple picture we can have for these kind of setups. Now, what I will show is, depending on the nature of the dark radiation, whether it is coupled or it is free streaming, the isocurvature perturbations, they can have distinctive effects on the CMB. Now, in particular, free streaming dark radiation, as one can expect, is quite similar to neutrino density isocurvature, and we'll see this fact more explicitly in a moment. But then for coupled dark radiation, you can have qualitatively different effects, and I'll highlight those. So I think the main takeaway messages for this entire talk can be summarized in the slide. So there are two key points. First is that I'll try to demonstrate that for isocurvature initial conditions, free streaming dark radiation actually leads to more CMB anisotropies than coupled dark radiation. And this is exactly opposite to what happens for the adiabatic case, where actually CDR or coupled dark radiation gives rise to more anisotropies. And this is something that you see on the figure on the right. Indeed, free streaming dark radiation or FDR, they indeed give you more CMB anisotropies when you start with isocurvature initial conditions. So this is a very this is exactly the opposite to the adiabatic scenario, and I'll explain this in a moment. The next important feature that I'll point out is that in general, both for coupled and free streaming dark radiation, having isocurvature perturbation helps with the H0 tension. And the basic idea is that once you add extra degrees of freedom, extra radiation, typically you can have some bit of silk damping at high L. But then if you have blue tilted isocurvature perturbation, you can have enhanced density perturbations at a high L. So what can happen is that this enhancement due to the blue tilt, it can compensate for the silk damping. And then that can give rise to, that can let you accommodate more delta N effective and give rise to larger H0. And this is again something that I'll explain after a few slides. So more generally, along with these two key points, I'll also give new constraints on coupled dark radiation isocurvature based on the latest Planck data, and also will update one existing study where they studied free streaming dark radiation, but then here we updated using the latest Planck data as well. Okay, so broadly speaking, these are the main takeaway messages, but then let me now get into more technical aspects of it. So to solve or to see the effects of these isocurvature perturbations on the CMB, you have to set up the initial conditions properly, and then you can feed them into a Boltzmann solver like class, and then you can get all the CL plots. So first I'll discuss how to set that up, and then I'll have some discussion about analytical discussion to distinguish FDR versus CDR, and then I'll talk about results, and then I'll conclude. So let me start with some of the notations. So as the name suggests, isocurvature perturbations are basically perturbations that do not give rise to curvature, okay? And it's sort of easy to illustrate it in the context of, for example, neutrino density isocurvature. So if you work in the synchronous gauge, then it turns out that for very early times, like deep into the radiation dominated universe, and for superhorizon modes, you have vanishing metric perturbations. But then also for isocurvature perturbation, what happens is that the total density perturbations also vanish. In other words, deep in the radiation domination, you only have neutrinos and photons. And what this quantity, what the vanishing of this quantity implies is that in a given patch, you can have an over density in neutrinos, but then at the same time that can get compensated by an under density in photons. So in the end, the total delta rho becomes vanishingly small. And because you have vanishingly small metric perturbations as well, in the end, you do not get any curvature perturbation at all. So with these kind of initial condition, you do see that delta rho nu itself can be non-zero, so can delta rho gamma be. And these set of conditions then define the isocurvature initial condition, which you can capture in a gauge invariant way by a variable like this, where I'm taking like delta nu minus delta gamma, where delta nu is basically delta rho nu over rho nu, and delta gamma is similarly defined. So broadly speaking, that's how isocurvature is defined. We of course know that all the perturbations are mostly adiabatic, because otherwise the CMB spectrum would have looked very different. So now to move over to dark radiation isocurvature, one can proceed in an analogous way. So one can again work with the synchronous gauge and demand that the total delta rho is equal to 0 at very early time, so that you don't have any curvature perturbation at all. But then we also do not want any neutrino isocurvature, because our focus is to study dark radiation isocurvature. So for that purpose, we set delta gamma to be equal to delta nu. And once you specify all of this, it turns out that if you choose a normalization of delta dr to be equal to 1, the other density perturbations, they're uniquely determined. And these set of perturbations then determine the unique initial condition for the density perturbations. And I should mention, of course, that here you should assume that like the usual 10 to the minus 4, 10 to the minus 5 factors, they are just factored out from this. So here we are just focusing on the ratios if you want. All right, so till now, there is no distinction between CDR versus FDR. All the deltas are identically related to each other for both the two cases. But then once you go over to other quantities, because of the non-zero anisotropic stress in the case of FDR, you start to see interesting differences. So I won't be going over this slide in much detail, but what we do is the following. So I just told you how to set initial conditions in deltas, but of course, to solve the full set of coupled Boltzmann-Einstein equations, you need the initial conditions for other quantities as well, like photon velocities, density perturbations in baryons and CDMs and so on. And to do that consistently, you have to take into account all the relevant equations, and then you go to the superhorizon limit for a given K mode, and you go deep into the radiation dominated era, and then you solve all of these equations order by order in K tau and omega tau, where K tau is a small number, it characterizes the superhorizon limit, and omega tau being small, it tells you the fact that you are deep in the radiation dominated era. So I won't be going over all the details, but I'll just mention that for CDR, of course, we turn off the anisotropic stress term, so you cut off this equation. So once you go through this solutions, which we have done, you start seeing you can list all the initial conditions that you can then feed into a Boltzmann solver. Now, again, I won't be going over all the details, but very quickly speaking, I can mention two interesting facts. First is for FDR, as you can expect, this really matches with neutrino density isocurvature. This is not a surprise because neutrinos are, of course, also free streaming. So this is indeed a good sanity check for our setup. But then once you go over to CDR, you start seeing some interesting differences. And that basically comes because for CDR, the anisotropic stress is 0. In particular, you see that there is a sign difference for this eta parameter, which is basically one of the metric potentials in the synchronous gauge. So let's try to see what the implications of this in a more physical way. So let's try to do some analytical calculations to see how this manifests itself, how we can have a difference between CDR and FDR. Now, before jumping into that, let me just take a super quick detour and then focus on the adiabatic initial conditions for a moment. Now, this case is well known. Here, like because of the adiabaticity, all the species, they follow the same density perturbations, say from the inflaton. But then what happens for FDR is that because of free streaming, FDR, they stream out of gravitational potential wells. And as a result, the metric potentials become smaller in magnitude, and in turn, they source smaller CMB anisotropies. On the other hand, for CDR, what happens is that this free streaming effect is no longer there, and thereby they can source larger metric potentials, and correspondingly, you get larger CMB anisotropies as well. This, of course, you can compute by computing a Sachs-Wolf-like term and the initial condition of it, and then you indeed see that turning on some free streaming dark radiation indeed decreases the anisotropy. And of course, that's also what is shown in the plot on the right. Now let's see what happens for the case of isocurvature initial condition. So in this case, I won't be going over the derivations, but you can show that in this case, the total anisotropic stress of the entire system is basically dependent on the overdensities in the free streaming radiation. And this is not really a surprise because that's the only thing that can contribute to sigma. Here, delta Fs is a weighted sum of the individual delta i's, where I runs over all the free streaming species that you have. Now let's look at what happens for isocurvature initial conditions. Now I mentioned that for this, we have a compensation going on. So if you have an overdensity in dark radiation, then that corresponds to an underdensity in photon and neutrinos, right? So now let's look at CDR. So for CDR, what happens is that only neutrinos free stream, right? Because dark radiation is coupled. But then because only neutrino is free streaming, the only quantity that contributes to delta Fs is delta nu itself. But then I just told you that we have an underdensity for neutrinos. And therefore, what it means is that the net sigma, that is negative if you start with an overdense dark radiation region. For FDR, however, the exact opposite is true, because in this case, dark radiation also free streams, and therefore delta dark radiation also contributes to delta Fs. And because of the overdensity in dark radiation, sigma is actually positive. So you see that the primary difference between the CDR and FDR, it basically relates the fact of that there is a sign flip between the total anisotropic stress. To see how this manifests itself in the CMB spectrum, you can look at the metric potentials. You can use the fact that sigma is a gauge invariant quantity, and you can go to the Newtonian gauge. And from that, you can derive a relation like this, that phi plus psi is basically determined by sigma. This is sort of similar to the Einstein equations that we have like this. So now, as I just told you, that for CDR we have a negative sigma, and that corresponds to a positive value of this guy, and exactly opposite is true for free streaming dark radiation. So now, finally, let's translate all of this into the photon perturbations, because that's how the dark radiation can communicate with the photon perturbations via the metric perturbations. So for that, you can again look at the Sachs-Wolf term, and you can write it in terms of the gauge invariant photon perturbations and this combination of the metric potentials that I was just discussing about. Now, I also told you again that for dark radiation isocurvature, we are choosing an initial overdense region in dark radiation corresponding to some underdensity in photons and neutrinos. And that basically translates into a negative zeta gamma. And what that implies is that for CDR, because of this sign, you actually have a smaller magnitude of this quantity, and therefore you have a smaller anisotropy for CDR. However, for FDR, phi plus psi is negative, so is zeta gamma. Therefore, you have a larger magnitude of this quantity, and therefore you have more anisotropy. This is also reflected in the figure over here. But then you can also see it in the final CLTT spectrum as well. So here I'm plotting the spectrum for both CDR and FDR, and you indeed see that FDR gives rise to larger anisotropies. And it also shows that NDI matches with FDR, which is a sanity check for our setup. Now, let me also talk about how all of this is related to the H0 tension. So I just told you that for CDR, you can have less like the spectrum is smaller. So therefore, what can happen is that you can hide more isocurvature in CDR. And in particular, in general, in the presence of blue tilted isocurvature, the growth of perturbations at high L can compensate for the silk damping. And therefore, generically, both for CDR and FDR, you can accommodate larger ineffective. And in the end, it is this larger ineffective that gives rise to larger H0. Okay, so let me now talk about the results. So here are some quick details about our MCMC scans. The quick point is that we have 4 extra parameters, the number of degrees of freedom in neutrinos, in dark radiation, and also the isocurvature amplitudes. But here's the final result. So generically speaking, so here I'm plotting red, but I'm plotting CDR in red and FDR in blue. And generically speaking, you see that for CDR, you have larger isocurvature perturbation, and that is expected because I just told you that CDR gives you less anisotropy, so you can hide more isocurvature in CDR. So that is what is seen here. And also, generically speaking, CDR also allows you larger delta N effective as well. Now let's turn on the blue tilt of the isocurvature aspect as well. And because of the compensation between silk damping and the growth that I just mentioned to you about, generically you see both for FDR and CDR, once you turn on isocurvature perturbation, you see that all the green shaded regions, they are shifted towards the right and towards the top, indicating a larger H0. And in particular, CDR allows for the largest H0 that we can accommodate in this setup. And in particular, it reduces the tension with the local measurements of H0 to 1.5 sigma. All right, so I can now conclude. So I hope I have given you some flavor of these main ideas. And of course, I'm very happy to discuss more in the discussion session. But just to summarize, the points are that FDR gives you larger CMB anisotropy compared to CDR. And therefore, this means that you can hide more CDR in the data, more CDR isocurvature, that is. And then once you also take into account the fact that blue tilt isocurvature perturbation can help relax the H0 tension, all of these facts combined, it tells us that CDR isocurvature can give you the largest H naught you can have. And in particular, it can reduce the tension with the local measurement up to like 1.5 sigma. So yeah, with that, these are just the basic features, and of course, along with all of this, we have also have the full results for the MCMC constraints both for CDR and FDR.